Hi, my name's Andrew McLaren, and I want to help you out with problems where you have something moving at constant velocity, another thing moving at constant acceleration, trying to figure out when they get to the same distance or how much time it takes for one to catch up to the other one. This is probably one of the most common examples of a physics test question that you would see in an intro physics course in college. I remember specifically this question being on my own exam and talking to some of my students about this that I tutor, and multiple of them have confirmed that yes, this type of question is on the exam. It's a bit easier than some other questions, but it requires that you have some understanding of these equations and how to put them together. So the basic idea here is that you've got some sort of vehicle, maybe we call this the car, that is going to be accelerating, and it's going to have a constant rate of acceleration. So the car is accelerating and it's doing so at a certain rate. And then we've got this truck and it is going to be traveling at a constant velocity. So this truck is going at its constant velocity. And at some point in time, we're going to have this truck just kind of going quickly. This car starts off kind of slow, but then speeds up, and eventually they're going to be at the same distance. So to set this up, what you want to do is think about the position equation. Now in the full form of this would be having an acceleration and a velocity component in figuring out how far these things travel at any given moment of time. But the nice thing about having just constant velocity and just constant acceleration is that the formula gets simplified down. Because the truck right here, its acceleration is 0, then we can just ignore that whole component. That just is not something that we need to keep track of, because 0 times any number will be 0. Same with the car. If it is going at constant acceleration, but it's starting with a velocity of 0, we can just kind of eliminate those two things from the equation. Now, the interesting thing is that these two cars, when they've caught up to each other, they've gone the same amount of distance. So the change in x is constant between these two. We don't know what that distance is right now, but we can assume that it goes the same amount of distance over the same amount of time. So we can set those two equal to each other, this change in x being equal to both this acceleration times its time squared for the car, and that is also now going to be equal to the velocity of the truck times time. And this might look a bit tricky at first. We do have the velocity and the acceleration. Luckily for us, we can divide both of these sides by t and eliminate it. So now we've just got v naught being equal to a times 1t all over 2. And we have all of these components besides t in this new equation. So we should be able to solve for t by itself by plugging these in. So we've got our velocity of the truck. We said it was 7.5 meters per second. And that is now going to be equal to the acceleration of the car, which is 2.35 meters per second squared times some amount of time all over 2. We just do a little bit of math here, and we should be able to isolate for t and solve for it. I would also suggest that we plug it back in at the end, so I will be doing that as our final step here. But to get t by itself, we take that 7.5, times that by 2, and then divide that by the 2.35. So our time is 6.38 seconds, right there, which means we should be able to now plug that back in into these earlier equations and figure out how far it's gone. So if we take our truck's equation right here, and we think about that now at that given amount of time, at 6.38 seconds, and it was traveling at, I believe it was 7.5 meters per second. So the amount of distance that this thing has traveled is just those two numbers combined. This, so it's 47.85 meters. And we actually should do a little rounding here. So this time, if we were just trying to report out a number, it was limited to 2 sig figs. So it really should be considered 6.4 seconds. I'm going to use this raw number down below because if we want the math to just do math, we are going to use this unrounded number. It should give us something more precise in that mathematical relationship. But if we're trying to look like sig figs, we need to look at how accurate the inputs were to tell us how accurate the output can be. So we can do the same sort of plug in with this equation to confirm how far it's gone, but they should have gone the same amount of distance in the same amount of time if our math has been done correctly. So we have the acceleration, which was 2.35 meters per second squared. And we're timesing that by the time squared, and the time we said was this 6.38 seconds. And that is all over 2 as well. So we just take that 6.38, we're going to square that, and then we're going to times that by 2.35 and divide that by 2. And we're getting very close numbers. This is 47.827 meters. If we're looking at how accurate these numbers really are, it's limited to 2 sig figs from our earlier answer or input earlier. But right now I'm seeing a 2 sig figs number. So this really should be limited to 48 meters. And yes, this other number, we wrote it out as 3 decimal places, but it's really only accurate to 2 because we got that number from combining something that was only accurate to 2 sig figs. So this should also be only 48 meters in terms of its level of accuracy. I could be using the 6.4, but by squaring that number, you might get something a little bit bigger to the point where it's no longer 48 and 48 meters. So if you want the math to just have math out by getting the same output as input, you want to use these raw numbers. But to talk about this level of precision, we should be limiting this problem to 2 sig figs because the provided numbers were only that accurate. You can think of it as like they were potentially 10% off, not 1% off. So we've got to limit our final answer to that. So that's the big picture on these types of problems. I can almost guarantee you this will be on an exam if you're in an intro physics class in college. High school teachers like it as well. They consider it a challenge problem, but this is not got any calculus in it. And most calculus physics classes will require you to understand that calculus stuff, but they won't actually really assess you on it. It's going to be more problems like this.